So, now we will go for the inductance of transmission line, the basic concept, right. So, we know that a conductor when carrying current has a magnetic field around it, right. For example, suppose if we apply right hand rule, suppose if this is your conductor, right, and if you wrap the conductor in the like this, then if this is the direction of the current flow, then this is that anticlockwise. If you see that anticlockwise, this is the direction of flux lines, right. So, whenever a conductor carrying current, it has a magnetic field around it, right. So, the magnetic lines of force are concentric circles, right, having their centers at the center of the conductor. If this is the conductor, then they are concentric circles, right, and they are centered at the center of the conductor. So, if I wrap it like this, and if this is the direction of the current, the thumb, the upwards, then you will have the magnetic field, right, but they are concentric circles actually, and their center will be at the center of the conductor, right. So, the voltage in that conductor, right, induced in the conductor can be written as E is equal to that your d phi by dt volt, right. Everywhere wherever possible I have written the units, right. So, it is E is equal to d phi by dt volt. This is actually equation number 4, right, where psi represent the flux linkages of the conductor in Weber turns. This is Weber turns, right. So, this equation 4, it can be written in this form, right, in this form it can be written. So, it is E is equal to d psi by dt. If you make it like this, E is equal to d psi upon di into di upon dt is equal to, you write down L into di upon dt. This is equation 5, where L is equal to d phi by di, right. So, that means L actually is a constant of proportionality, it is basically inductance, right. So, for a linear, when L is equal to d phi, L is equal to d phi by di is the inductance in Henrys. In a linear magnetic circuit, right, flux linkages vary linearly with the current, right, such that the inductance always remain constant, right. So, if the magnetic circuit is linear, then instead of flux linkages vary linearly with the current, therefore, inductance always will remain constant. That means, this L is equal to d phi by di, we can write L is equal to psi by I in Henry, right. So, as it is linear magnetic circuit, so we can write like this, that L is equal to psi by I, right. So, inductance will remain constant. So, it is in Henry. So, this is given equation number 6, right. So, actually one more thing I would like to tell that look, actually lambda symbol is like this, right, but my habit has become to write lambda like this. So, throughout this I have to use this, right. So, so there should not be any symbolic change or anything. So, this psi actually we use lambda, see this thing as a flux linkages, right. So, equation 6 we can write that lambda is equal to L, actually lambda is equal to psi, right, flux linkages, but representing it by lambda now, right, and lambda and psi are the RMS values of the flux linkages and current respectively. These are the RMS values, and this is equation 7, right. So, making use of Ampere's law, if you making use of Ampere's law, which relates magnetic field intensity H and to the current enclosed, that is I suffix is enclosed, current I enclosed, right, and relates magnetic field intensity H, then loop integral, this integral one, this is called loop integral, H into dl is equal to I enclosed, right. So, that means this is your Ampere's law that you know from physics, right. So, this is equation number 8, right. At the same time, because later this equation will be used, right. Now, the flux density, right, that is in Weber per meter square, right, is given by B is equal to mu into H, that you know, right. So, this is equation 9 where mu is equal to mu 0 into mu r, and mu 0 is equal to 4 pi into 10 to the power minus 7 Henry per meter is the permeability of the free space, and mu r is the relative permeability, right. So, what we can do is, so replace d by dt in equation 4, that means this equation 4, that means this equation, right, you replace d by dt, right, by j omega, and psi, instead of psi I said psi and lambda both are same you take, right. So, in that case, that in equation 4 if you replace d by dt by j omega, the steady state AC voltage drop due to alternating flux linkages can be obtained as that V is equal to j omega Li, that is j omega lambda, lambda is equal to Li, right, psi is equal to lambda, lambda is equal to Li. So, this voltage drop will be V j omega Li. So, j omega L is nothing but that your reactance, right, and I is the RMS value of the current. So, that means j omega and Li is equal to your flux linkage lambda. So, V is equal to j omega lambda. This is actually equation 10, right. Now, similarly, if you want to find out the mutual inductance between two circuits, it is defined as the flux linkage of one circuit due to current in the second circuit, right. So, it may be given as generally it is that is M21, later we will see for the when we will take the your conductor, if to find out the inductance of the single phase 2 line and other things, conductors inductance, at that time we will see that mutual inductance also. So, in that case, that we can write M21 is equal to lambda 21 upon I1, right. That means this is that mutual inductance, it is Henry, it is your equation number 11 is given, right. So, the mutual flux linkage between two circuits defines the flux linkage of one circuit due to current in the second circuit, right. So, that means this is the flux linkage, this thing due to the current of the second circuit, due to the current in the your what you call due to current in the what is this between two circuits, it defined as the flux linkage of one circuit due to the current in the second circuit. So, this is if lambda 21 upon I1, that is your flux linkage of one circuit due to the current in the your second circuit due to the current into the first circuit, that is first circuit current is I1, right. Now, therefore, if you find out this, because of this mutual inductance, what will be the voltage drop? So, voltage drop in circuit 2 then due to the current in circuit 1 is given by V2 is equal to j omega, same as before, into M21 I1, right. So, j omega will remain as it is, but lambda 21 is equal to M21 into I1 volt, right. So, this is the voltage drop in the second circuit. So, this way we can determine that mutual inductance, but details we will see later, right. Now, inductance of a single conductor. So, transmission lines are, that is why every step I have written it here such that we should not miss anything. So, transmission lines are composed of parallel conductors and can be assumed as infinite long, because if you have seen the overhead transmission line, we can assume they are parallel conductors, right, and it can be we assume that they are infinite long. So, based on that we will develop expressions for flux linkages of an isolated current carrying cylindrical conductor. We will assume that conductors are of cylindrical type, right, solid conductors, right, with return path lying at infinity. That means, we will see that your what you call isolated current carrying cylindrical conductor and return path is lying at infinity, means this will complete a single turn circuit, right, based on this assumption. And magnetic and your what you call and magnetic flux lines are concentric closed circles with direction given by the right hand rule. I told you at the beginning that if this is the your vertical thing, that conductor, and if you wrap the conductor like this, and if this is the direction of the current, then this will be the flux lines, right. So, with direction given by the right hand rule. So, next is to calculate the inductance of a conductor, it is necessary to consider the flux inside the conductor as well as the external flux, both internal as well as external, both the flux linkages we have to consider to determine the inductance of a single conductor, right, current carrying conductor. Now, internal flux progressively links smaller amount of current as we proceed inwards toward the center of the conductor. For example, say that this is the cross sectional view of the conductor, right, and it is carrying current. So, now when we proceed and we assume that uniform current density, we assume uniform, and we proceed, suppose this is the center, from this surface actually if you move toward the center, right, then what will happen, it progressively links a smaller amount of current, because we are assuming the current density, say it is uniform, right, we are assuming that. Therefore, as we move like this, then that means your internal flux progressively links, suppose if you make all internal flux line, all internal, I mean I am making it like this, suppose you make all internal flux line like this, So, as you move from this one towards the center, then it progressively links smaller amount of current, right. So, that means it is written here, as we proceed inwards towards the center of the conductor, right. So, an external flux always link the total current inside the conductor. External flux means this is that is outside the conductor. If this is the conductor, then outside the conductor. So, it will always link the total current in the conductor, right. So, based on this we will try to find out what will be the internal your what you call that inductance first. So, suppose this is your figure 1, right, and this is your conductor, right. It is a long cylindrical conductor, and this is the cross sectional view, and its radius is actually r, right, and you consider at a distance x, right, a small your infinitesimal small that length dx, this is your dx, and this is the arc length, is very small one, it is actually dl, right, and from here that electric field intensity at a distance x, because from here x, here it is x, it is a circular path. So, from here say you assume that is your what you call that your magnetic field intensity is hx, right. So, this is a cross sectional view of conductor, this is the radius r, and at a distance x we consider a small very small this thing your with dx, right, and this is that your length dl, this is your what you call the arc length dl, right. So, in this case what we will do, that the MMF around a concentric closed circular path of radius x, this is a concentric closed circular path of radius x, right, internal to the conductor as shown in figure 1. So, this is your figure 1, this is figure 1, right, and therefore, the loop integral you can write in that hx into dl is equal to Ix. Suppose at a distance x the current is say Ix, right. This way you define, then where Hx is equal to magnetic field intensity, that is ampere turns per meter at a distance x meter from the center of the conductor. So, here also it is x, here also it is x, right, at a distance x from the center of the conductor, right, and Ix is equal to current enclosed up to distance x. So, Ix is equal to current enclosed up to this distance x, right, is ampere, right. Since the field is symmetrical, as the field is totally symmetrical, that Hx is constant at every point, right. So, Hx is constant for all points equidistant from the center. So, as the field is symmetrical, so it is a circular path. So, everywhere Hx will remain constant. So, if it is so, then if Hx remain constant, then this dl, integration of this dl, actually it will be the total circumference, that will be your 2 pi x, right, that is your 2 pi x, and Hx is constant everywhere. So, into Hx, this integral actually is equal to into Hx is constant at everywhere. So, Hx will remain as it is, and dl it is this is the total arc length, but if you take the total circumference integral of that loop integral, then it will be 2 pi x into Hx is equal to this current, your what you call is equal to Ix, right. So, this is equation 14. Now, So, we will neglect skin effect, we will neglect this and assuming uniform current density, that means at that if you take the cross section, we will take the uniform current density, right. So, at a distance x, just hold on, at a distance x, right. So, this area of this circle is pi x square and at a distance r, area of the circle is pi r square. So, at a distance x, current is I x. So, current, we will assume that current density is uniform, therefore, I x upon pi x square is equal to I upon pi r square, right. Therefore, I x is equal to pi will be cancelled on both sides, I x is equal to x square upon r square into I, this is equation 15, right. So, after this, from equation 14 and 15 we obtain. So, in equation 14, here it is. So, equation 14, right, in equation 14 you substitute I x is equal to this one and small simplification, this H x will become that I upon 2 pi r square into x ampere turn per meter, right. So, this is equation 16. So, for a non-magnetic conductor with constant permeability mu 0, the magnetic flux density Bx at a distance x from the center is, right. Therefore, again the for a non-magnetic conductor with constant permeability mu 0, right. So, at a distance x, what will be my Bx, that flux density, right. So, in this case what you can do is that Bx is equal to, actually Bx is equal to your mu 0 into Hx and Hx is equal to I upon Hx is equal to I upon 2 pi r square into x. So, mu 0 into I upon 2 pi r square into x, right. So, this is equation 17, right. So, where mu 0 is the permeability of the free space or air, right, and is equal to 4 pi into 10 to the power minus 7 Henry per meter. So, now the differential flux d phi x for a small region of thickness dx, that means this one, this diagram again, right. So, differential flux dx for a small region of thickness, this is thickness is dx, this is dx, right, and 1 meter length of the conductor is. So, the small differential flux dx d phi x is equal to bx into dx into 1, it is something like this. I hope you will be able to, suppose you fold it, suppose this is your conductor, this is a conductor, suppose this length is 1 meter and you have this thickness is dx, right. This thickness, if you fold it, then this thickness is dx and this length is 1 meter. So, area will be this portion dx into 1 square meter, right. I think you have got it. So, that means that d phi x is equal to dx, that is the flux density wave per meter square into this area dx into 1, right. So, that is why the differential flux d phi x for a small region of thickness dx and 1 meter length we are considering of the conductor is d phi x is equal to bx into dx into 1, that is bx is equal to mu 0 I upon 2 pi r square into x, right, into your what you call dx. So, this is equation 18. So, the flux d phi x actually links only the fraction of the conductor, because it is at a distance x, right, it is at a distance x only. So, it links that your fraction of the your conductor, right. Therefore, on the assumption of uniform current density, therefore, on the we have assumed the current density is uniform, right, only the fractional turn we call reality, this there is no turn because it is cross sectional of conductor, but only the fractional turn of the total current is linked by the flux, because at a distance the area is at a distance x, area is pi x square and conductor radius is r. So, its radius is pi r square. So, we call this ratio pi x square upon pi r square as a fractional turn of the total current is linked by this flux, right. This way we imagine. So, in that case then what will happen, then flux linkage will be, this is the fractional turn. So, flux linkage will be d lambda x into, this is actually fractional turn, right, into d phi x, right. So, x square upon r square, pi cancel actually, x square upon r square into d phi x. So, d phi x is equal to, we have seen that mu 0 by the d phi x is equal to, here it is mu 0 I upon 2 pi square into x into dx, substitute, then you will get that d phi x is equal to mu 0 into I divided by 2 pi r to the power 4 into x cube dx. This is equation number 19, right. Now, as the conductor radius is r, so integrate from 0 to r, right, then you will get the total internal flux linkages. So, lambda internal is equal to 0 to r mu 0 I 2 pi r to the power 4 into x cube dx. So, you integrate and this will be mu 0 into I upon 8 pi Weber turns per meter after integrating, right. So, you will find that it is independent of r, right, there is no r because it will come to r to the power 4 upon 4. So, r to the power 4 will cancel, right. So, this is equation 20, that means lambda internal actually is equal to, we can mu 0 is equal to 4 pi into 10 to the power minus 7 Henry per meter square. So, we substitute here 4 pi into 10 to the power minus 7 divided by 8 pi into I Weber turns per meter square, right, or lambda internal is equal to half into 10 to the power minus 7 into I Weber turn per meter, right. So, lambda internal, this is the flux linkage per meter. Therefore, inductance internal is equal to lambda upon I. So, L internal is equal to lambda internal upon I is equal to half into 10 to the power minus 7 Henry per meter. That means, this internal inductance of a current carrying conductor, alternating current carrying conductor, right, is half into 10 to the power minus 7 Henry per meter, and it is independent of the radius or diameter of the conductor. That means, whatever may be the diameter of the conductor, right, or radius of this thing, radius of the conductor, whatever may be radius or diameter, this L internal is always a constant value, that is half into 10 to the power minus 7 Henry per meter square. This is I have marked on equation number 21. So, that is the internal inductance of a current carrying conductor half into 10 to the power minus 7, right. Next one is that inductance due to external flux linkage. So, this is the cross sectional view of the conductors, right. So, what we have taken? We have taken this radius of this conductor is r. We have taken two external point, one is at P, that is from the center of the conductor, the distance is d1, this from the center of the conductor to this point P, distance is d1, and another point we have taken Q and the distance is d2, right, and we have taken this thing, right, d2, and these 2 points are external, these are the flux line we have taken, right. So, now, so that this is figure 2, flux linkages between two external points P, Q, right, P and Q. So, that is why I have written here figure 2 shows 2 points P and Q at distances d1 and d2 from a conductor which carries a current I ampere. So, current carrying by this conductor is I, right. Since the magnetic lines of flux are concentric circles, all this line of flux are concentric circles around around the conductor, whole of the flux between points P and Q, right, within the concentric cylinder surfaces, right, which pass through these points, right. So, all are concentric, right, in between this point is taken Q here, P here. So, in between Q and Q point, whatever the flux lines, they are concentric, right. So, the field intensity at a distance x, right. So, we have taken at some distance x external to the conductor, of course, this x is external to the conductor. So, the field intensity at a distance x can be given as H x is equal to I upon 2 pi x. We have seen that any point this magnetic field intensity H x will remain constant because it is a concentric circle, right, and at a distance x the circumference is 2 pi x. So, I is equal to, and conductor is carrying current I. So, H x is equal to I upon 2 pi x is equal to ampere turns per meter. Wherever possible, I have given your units, right. This is equation 22. Now, and the flux density just we have seen at a distance x, Bx is equal to mu 0 into Hx. So, mu 0 Hx is I upon 2 pi x, this is Weber per meter square, this is equation 23, right. So, the flux outside the conductors link the entire current I at the beginning I told, right, and hence the flux linkage d lambda x is numerically equal to the flux d phi x. Here no question of fractional term will come because it is external to the conductor. So, numerically d lambda x and differential flux d phi x both are same, right. Therefore, the flux d phi x for a small region of thickness dx, that small region of thickness dx, the flux differential flux d phi x here, right, and we consider 1 meter length of the conductor is given by d lambda x is equal to d phi x, both are same, is equal to bx into dx into 1, because same concept of this area, right. This is your, if you imagine like this cylinder, this thickness is dx and this length is 1 meter and this thickness is dx, right. Then if you fold it, then this thickness and this one dx into 1, the cross sectional area, right. So, in this case same as before, d lambda x is equal to d phi x is equal to bx into dx into 1 is equal to, you substitute bx again, mu 0 I upon 2 pi x dx, this is Weber per meter, right. So, this is equation 24. Therefore, the total flux linkage of the conductor due to flux between points P and Q we have to obtain. So, distance of point P from the center of the conductor is d1 and point Q is d2. So, what you have to do is you have to integrate this, right, that means lambda pq, right, between these 2 points, integration limit is d1 to d2 mu 0 into I upon 2 pi x into dx is equal to mu 0 I upon 2 pi, and if you integrate it, it will be natural log ln d2 upon dr d1, right. This is equation 25, right. Therefore, the inductance between 2 points, that is P and Q, external to the conductor, is then given by L external is equal to lambda pq upon I. So, lambda pq is this much divided by I, means this I will be cancelled. So, it will be mu 0 upon 2 pi natural log ln d2 upon d1 Henry per meter, right. And if you substitute mu 0 is equal to 4 pi into 10 to the power minus 7 Henry per meter, if you substitute mu 0, then 2 pi will be cancelled, right. So, ultimately it will be Lx it will be 4 pi divided by 4 pi into 10 to the power 7 divided by 2 pi, that means L external will be 2 into 10 to the power minus 7 ln d2 upon d1 Henry per meter. This is your equation 26, right. So, that means what we, in this case we can see that L external case, it depends on that your what you call, later we will see that from center of the your conductor to some distance d how things will happen, but if you have 2 points d1 and d2, right. So, L external is function of this your both the distance d1 and d2, right. So, it is dependent on the distance d1 and d2, later we will see how we will simplify further, right. So, next one is that inductance of a single phase 2 wire line, right. For example, before this thing, that suppose you have taken that your single phase 2 wire lines, right. So, this is one conductor, that red one, this is another conductor, we assume its radius is r1, its radius is r2, it is your current I1 and plus means the current entering into the page of the conductor, right. That is why plus thing is given, this is return path, dot is showing, that means current leaving the page, right, and distance between these two conductor is d, right. So, this is single phase 2 wire system. So, one is carrying your current I1, that is leaving into this thing, and this is return path actually, right, and we have to find out that inductance of a single phase 2 wire line.